Good day once again, class. Welcome to our another session of differential equation. And now we are already on the application. So first application that will be tackled is more on geometric application. So here, I'll first tackle the basic geometric applications. Okay. So we have three examples here of geometric applications. In geometric application, therefore, you need to recall your analytic geometry, uh, the identities, the principles of geometric or analytic geometry. Okay, so don't worry, you will be guided as we go on. Okay, so from here, let's start. So in geometric application, we have the first example. Okay, so the example states that find the curves such that part of every tangent between the x-axis and the point of tangency is bisected by the axis. Okay, plus the given is just only this. This one is the solution. Okay, so if you're given with this problem, you are actually looking for an equation. So you are trying to find an equation for this given problem. Okay, so find the curves of such that part of every tangent. So let's recall. So when we talk about geometry, we tackle with the topic slope. Okay, so let me choose first. Okay, so I'm sure you've discussed slope. Okay, and we know that slope is rise over run, right? And in analytic geometry, slope, we know it with a symbol m, which is equivalent to tangent theta, right? That is for in analytic geometry. Diba? Okay. Now, let's try to analyze the problem. Okay? Let's try to analyze this one. Okay. So, the problem states that find the curve. So, from this one, so we have actually, we could say that we have a family of curves. We can have as many curves as we want, right? We don't know what curve this problem is talking to. So let's just make a general assumption. So let's say we have a curve here, okay? Let's say we have a curve, sorry. Let's say we have a curve here. And then it states that find the curve. So meaning you are looking for the equation of the curve such that part of every tangent, and we know that when we talk about tangent, it talks about the slope and rise over run. And when we talk about rise over run, we always look at this figure. This is your y, this is your x, right? And this is your rise, and this is your run, right? And this is your slope. Okay? So, you have this one. So, you will have a slope here. So, from here, your m is your slope. So, from here, you could analyze that this one is your tangent line. So, this is your tangent line. So, meaning, find the curve, so this curve, that is part of every tangent. So, if we have here, so part of every tangent, meaning this curve is a part of a tangent. So, it passes through it, okay? Because we could look at here that the point of tangency. So, therefore, we have a point of tangency. Okay, this is your point of tangency. This is your point of tangency. Okay, this is a point of tangency. Okay, now it says here also that the point of tangent from the point of tangency, so let me, okay, so let's say we have this figure. So from this point of tangency, so it is bisected by the y-axis. So bisected means it is divided into two. So let's say it is bisected by y-axis. So this is your y-axis. It is bisected, so it is divided into two. So this, therefore, this is your x-axis, right? If this is bisected by the x-axis, sorry for the figure. So bisected means it is divided into two equal parts. So this is an x and this is a value of x, which we don't know. So maybe this one until here is equivalent from here until here. Sorry for the figure. Okay. So meaning we have x here and we have a rise that we don't also know. So from there, we could look into, okay, so as I've told you, our slope in analytic geometry is equivalent to rise over run. But in differential calculus, if hopefully you still remember your differential calculus, it states that from differential calculus, the slope of the tangent line, so the slope of this tangent line is equal to the slope of the curve. So the slope of the curve is equivalent to the slope of the tangent line, which is equal to dy over dx, which is the rise over run. Alright? So in differential calculus di, the slope is equivalent to dy over dx. Okay? So now, in order to get the curve, the equation of the curve, you need to solve for the slope. So the slope given is dy over dx, which is equivalent to rise over run, right? Because that is the slope. What is the rise? That is the y. What is the run? That is duha ka x with equivalent distance. So 2x. Sir, why we don't put a value? Because we really don't know the value of this one. Wala ta kay baw ani. Kining distansya ha. We don't know that one. And also the value of x from here. We don't know it. So, and obviously here, we don't know it. So we represent it with a variable. So from there, we could just do variable separable, if I'm not mistaken. Right? So from here, we could have dy equivalent to, so transpose, you just dy, your y will be put here, dx, or cross multiply. So this is y, so dx over 2, sorry. So dx over 2x. So from there, so I could put the 2 in the other side. So in order for me, actually, this problem already has an answer, okay? So in the book, there is no solution, so I just get the answer. So this is a guide. So the answer is this one. So now we need to prove. So from there, you could also transpose or multiply the 2. So you have 2 dy over 2 dy over y is equivalent to dx over x. Now, since they are already separated, we can now integrate. So 2 ln y equals ln x plus ln c, obviously. So from there, you have You have ln y squared plus ln c, ln x minus ln x. So, or we could just have it like this because we have an answer like ln x, this is plus, so that is xc or cx. Okay, so cx, since this 2 is added, so apply logarithmic, so we have we need to multiply. So from here we have y squared equals e raised to the power of ln cx. So this becomes 1. So therefore your general solution is y squared is equals to cx. Okay, so this is your general solution. Okay, so actually in application of differential equation, in geometric application, so it is actually hard to analyze problem if you really don't know the identities, the principle of analytic geometry, solid mensuration, trigonometry. So it is very important here. But the most important is the geometry itself, the analytic geometry, because this is a geometric application. Okay, so this problem is solved and analyzed by using this analysis. Okay, so let's try another problem. So again, let me review you. So why did we come up here? Because the problem states that find the curve such that every tangent, so pangitaon lang nato ning equation aning curve. So therefore, this curve is equivalent to y squared is equals to cx. Okay? So because we could have it here, we could have it anywhere, but we have a clear instructions here that every tangent, so this is your tangent, because we know in the geometry the tangent, every tangent, so this is your tangent, so it represents the slope, right? So we know that tangent represents by m, which is rise over run, which is your slope, and the point of tangency, so meaning point of tangency, is meaning the tangent line intersects a curve. So that is the point of tangency. So that's why you need to recall your other topics from your other subjects. So from here, ang atoa daw point of tangency from here, o ang atoang tangent na between every tangent between x-axis is bisected. So gitunga daw nato using or bisected by the y-axis. So gitunga siya. So gitunga, so meaning kung gitunga, so equal, divided equally. So here, so sorry for this. So pag graph na ko na, dinalian na siguro na nako, I forgot to put it in equal. But the representation represent this one is equal to this one. So let me move it. Okay, so but here it is represented well. So this one and this one is equal. Okay, now after that we have two unknown variables here, x and y. So and we know that the x and y is the rise over run. So therefore that is the slope. And in differential calculus, because we cannot use the m because m represents slope and we are doing differential equation, we could only use similar variable. So we use derivative, which is to represent the slope, that is dy over dx. In differential calculus and equation, slope is represented by dy over dx. In geometry, it is represented by tangent theta. I think in other algebra, trigo, rise over run, and also analytic. So trigo, rise over run. So from here, we have to get because we